Okay, here we go. Good morning, good afternoon, good evening, wherever you are, whenever you are. Today we'll be installing telemetry via Wi-Fi so that we can communicate from our ground control station to the drone when it's flying in the air. As usual, I will tell you the specs of my machine. This is a file I've created so we can go quickly. It's Surface Pro. I think it's a Surface Pro 9. With a Intel processor, 16 gigs RAM. It's Windows 11 as of today's date, which is 29 August 2024. These are the programs that I've installed on here so far, and there have been some drivers installed when I installed those programs. So that's what we're starting with on this machine. So let's get started. So telemetry, what does that mean? That means two-way communication between the drone and the ground. And how does it work? We'll talk about that in a minute. But what does the drone and the ground control station, what do they say to each other? So they have to speak some sort of a language. Typically, the drone will give out its GPS position. It might give its throttle setting. It might tell you its orientation, its temperature. And then the ground control station will take that information from the drone and plot it on a map on your computer. And then the ground control station may send commands in the other direction up to the drone, for example, fly to some point, or rise or descend, or change your mode, or something like that. So they need to have a common protocol or language to talk to each other with. And that is called MAVLink. So we can go to the ArduPilot webpage, documentation, and we want developers to look into this MAVLink so I can explain it to you before we go on. So there's MAVLink interface, MAVLink basics. So MAVLink is a serial protocol most commonly used to send data and commands between vehicles and ground stations. Let me explain that to you in plain English. It's up to the system designer to allow bits to be passed between the drone and the ground control station. And those bits come bit by bit by bit by bit. How that happens, whether it's internet or USB or TC or UART, is not the concern of MAVLink. MAVLink is how those bits are interpreted by the sender and the receiver. So it's a protocol, and that's used for communication. And the first point of the protocol is that it sends packets between 8 and 263 bytes, and it typically sends them about 10 times a second, depending on how the systems are configured. And there's lots of different packets. One might be the GPS location, one might be the throttle setting, etc. So this is a detailed description if you're interested in further exploring of what the packet consists of. First byte is the start sign. The second byte is the payload length. Byte number 1, byte number 2 is the packet sequence. Byte number 3, 4 are about which drone ID you have, in case you have more than one drone in the air, like a drone swarm. Message ID is what kind of packet it is. Is it a GPS location? Is it a throttle setting, etc.? And then the data packet, the payload packet, can be up to 255 bytes, and then there's a checksum. Okay, so there's these packets going back and forth between the drone and the ground station. And actually, this is a good picture. One of the most important ones is called heartbeat. The drone sends it once a second just to let the ground control station know that it's alive. You can also have send and request commands. You can so we'll get into that. And then what else do I want to show you here? Oh, yeah. So the heartbeat is 1 hertz. Typically, GPS is sent at 10 hertz. And then you can configure it to send as much or as little information as you want. So let's look at the kinds of information by going to MAVLink. MAVLink.io. So it's not unique to RGPilot. Any flight control software can use MAVLink to communicate. It's totally agnostic as far as the firmware on the flight controller or the operating system or firmware in the ground control station. What are the messages? So there's hundreds of messages defined. Heartbeat is an important one. System status is an important one. System time, ping, etc. So we can go on and on and on. Let's find GPS. GPS is a very important message. Lat, lon, fixed type. So the GPS packet will have all of these in it. GPS status will tell you how many satellites are locked, etc. Scaled IMU, the inertial measurement unit, gives you your XYZ angle and your XYZ acceleration and so on. So there's lots and lots of possible packets that can be sent. Typically, GPS is sent 10 times a second by default. The heartbeat is sent 1 times a second by default. There's a few other things that are sent 1 times a second. And then that's the basics of MAVLink. So that's the language that we want to use to communicate between our ground control station and our drone. And all we have to do is set up some hardware and software to make that work. So that covers MAVLink. So as I said, you can do, let's see what, this communication mechanism between the drone and the ground control station can be any bit stream that you want. It can be TCP/IP, it can be UDP, you name it. As long as you have a way of getting bits from one to the other, you can make it work. And by the way, if I go back to MAVLink, there's one more thing I want to explain. MAVLink has a lot of code. So there's here's all the autopilots that support it. Here's all the ground control stations that support it. And then here's some APIs that support it. And then there's also libraries. So there's libraries for C, Python, C++, C#, Java, JavaScript, Lua, Objective-C, Swift, etc. So these libraries will take the packet of bits that you get, that your hardware gets, and that library will then take those bits and interpret them and present it to your code as a structured object or a struct that gives you the GPS coordinates. You don't have to decipher the bits yourself. They'll decipher the bits and convert it to a variable that's lat, a variable that's lon, a variable that's altitude, and so on. So all that work is done for you if you ever want to use MAVLink in any of your projects. So we don't want to write any code. We're not writing code. We just want to make the drone talk to the ground control station while it's in the air. So how do we do that? Well, we have to have the flight controller. There's these arrows. There has to be some way of sending bit data, okay? And actually, with Mission Planner, with a USB cable, that's exactly what we've been doing. So when we connect from the computer to the flight controller with a USB cable with Mission Planner is communicating via MAVLink. And all that Mission Planner is a way for you to click configuration things on the screen, and then it'll convert that into a message that it sends to the drone over MAVLink using the MAVLink protocol over the USB cable. So Mission Planner is basically just a GUI for you to present these messages and to format them in a user-friendly way, so you don't have to do command line interface. There are command line options for sending MAVLink commands via the command line. We won't get into that now. Mission Planner is basically doing that for you. So when Mission Planner is talking to the drone over the USB cable, it's using the MAVLink protocol. So that's actually what's going on under the hood when you connect with Mission Planner. So we want to replace that USB cable, which is a bit stream, with a Wi-Fi device. So how do we do that? Well, we're going to need then to connect some wires. So let's go to the board, flight controller board, and see how we're going to do that. So if we go to the page for our course and go to links, and there's many ways to get here, but we want to look at what exact wires do we need to do on the flight controller to connect to a Wi-Fi interface. And actually, let me do Dronebridge first, just so you know where we're going. So the particular implementation we're going to do today is Dronebridge ESP32, which is shown in this picture. So we're going to have our flight controller, which is a Maytech. It's going to connect to this microcontroller ESP32 over a UART connection. That has an onboard Wi-Fi transmitter and receiver. So over Wi-Fi, that's going to connect to your PC on the ground, and you'll use Q ground control or mission planner to interpret those packets. So MAVLink protocol will go over the UART to the ESP32 chip, and then that will translate it using this Dronebridge software on the chip to Wi-Fi as a MAVLink stream over Wi-Fi. So that's where we're going with it. So how do we get there? Well, we need to wire up this flight controller to this microcontroller ESP32 to the flight controller, and then we need to configure the flight controller. So let's start with configuring the flight controller and look at that. Each flight controller is different. So let's go to the flight controller that we have, open link. So this is the manufacturer data for our particular flight controller. And here's a picture of it. And you'll notice you can have up to 5 UARTs. So one of the reasons I picked this for you is that you can have many, many different peripherals. So this is one of them, which we're going to use. And here's a layout of the, well, let's see, we want to do specs. So the specs is up to 5 UARTs plus 1 extra UART, 12 PWM outputs, 1 I2C, etc., etc., etc. So we're going to use one of those 5 UARTs. Let's look at the layout. So you're going to be soldering connectors that you can easily plug in and unplug to these holes here later, or maybe you've already done it, hopefully. And we want to pick one of the UARTs. So this tells us which actual connections we need to do for the UART. And we're going to be using RX and TX1. These two connections here, one's for transmit, one's for receive for the UART. We're going to use number 1, UART 1. I'll explain why in a moment. And then we also have, as a convenience, 5-volt and ground to power our microcontroller. Just as an FYI, we're using number 2, UART number 2 for our radio receiver, which we've already covered. And we're using UART number 5 for our GPS, which hopefully all of those you've already done. If not, that's okay. That can be done in a different video. Okay, so that's the picture of the board. Now, ArduPilot has a way, that board can run ArduPilot, Betaflight, lots of different kinds of flight controllers. So the manufacturer, the ArduPilot tells you if you buy that board or that family of boards, this is how ArduPilot recommends that you configure it. So there's 4 different boards in the family. We're using the WMN board. The WMN board has 5 UARTs, 12 PWM, 1 I2C, 1 buzzer, 3 ADCs, no SD card, USB remote, yes. So we are interested in telemetry. So I think you can use any UART for any function, but ArduPilot recommends this particular set of functions, and we're going to go with their recommendations. You're welcome to try changing this on your own, but this is a configuration that works for me. So here's the UARTs, UART 1, 2, 3, 4, 5, 6. There's some reason they're called serial 0 through 6. I don't know why they don't have the same numbers. And then these are the functions. Then if you have a GPS, typically use UART5. So that's why our GPS is connected to UART5. In telemetry, 1 is UART1. USART and UART, I don't know the difference, but they're basically the same thing from my point of view. So telemetry, we're going to use UART1. So that's why we're using UART1 for the telemetry. So we need to tell the flight controller how, let's go back to the Dronebridge picture. We need to tell our flight controller, that's our next step, how to talk to the ESP32. Well, that's our very first step, is to configure the flight controller. So let's do that. So we need to launch Mission Planner, of course. Then we need to connect via the USB cable for now, the Mission Planner, to the drone, which I will do by plugging it in. And I think we can do this without the battery. So I'm plugging the drone in.
Telemetry recovered.
It's got enough power to... let's connect.
Mode change to stabilize. Config error, Barrow, unable to initialize driver.
Okay, so I changed my mind. I am going to use the battery. The props are off. If I plug the battery in, I will make sure we have enough power to run all the peripherals. So the battery is plugged into the drone.
Config error, Barrow, unable to initialize driver.
Unhappy.
Mode change to stabilize.
Of course it's unhappy, so I'm going to do Control F and do a
Config error,
software
fix
reboot.
problem then reboot.
Software
Mode change to stabilize. Chan 3 to 9, PWM, failed, no DMA.
Shucks. Okay, ignore that error. So we are going to... okay, so we're connected now. The drone has power from the battery and from USB. If I move the drone around, you can see. So we need to check the configuration for the communication. So if we go back to the website, we're configuring the flight controller now so that it passes MAVLink data through one of the UARTs, UART1, to this microcontroller. And I do have a set of instructions, abbreviated instructions for this procedure. So let's go ahead and download that PDF file. So if we go to Files, Config Files, there's a set of abbreviated set of instructions called UCI Fall 2024 Drone Wi-Fi Telemetry. Let's download that. Open it. And we can zoom in. I'll show you that flight controller in a moment, but the first thing, well, let's pause and show you that flight controller. So that flight controller, okay. So I'm gonna go back a little bit based on these directions and explain that flight controller. They want to do that. No, we'll do that later. Okay, so I'll explain to you the hardware later. Right now, we're just going to configure it. I'll show you the pictures and we'll do all the specs later. So here's what we need to do for Mission Planner. We need to select a UART part and config serial XY to protocol MAVLink to baud 57K. That's all we got to do for Mission Planner. So here we are, Mission Planner connected to the drone, and I need to find serial, which is the UART. And like I said, we're using serial 1. So we want the op. Oh, is that correct? No, that's not correct because of this weird ArduPilot mapping. This is ArduPilot. Oh, yes, serial 1. Correct, RX1. We need to refresh the parameters, I think. Oh yeah. So we don't have any options. We're not doing anything fancy, but the protocol is 2. So serial 2 UART on the flight controller. Let me show you that for clarity. Oh, we want serial. Yeah, serial 1 is TX1, RX1. So these 2 pins on the circuit board are wired to the microcontroller, but the microcontroller doesn't do anything unless you tell it to. So we're going to tell the microcontroller via the mission planner configuration file that updates ArduPilot that's running on the microcontroller. We're telling the microcontroller send and receive MAVLink data on TX1 RX1. So serial 1 is TX1 RX1. The protocol we're saying is 2, which there's a drop-down menu here. These are all the protocols that you can have on that UART. And I don't have any idea what they all are, but we want MAVLink version 2. And the other thing we do is set the baud. I don't know how critical that is. If the baud is set mismatched, it may not connect. So let's choose 57K. That's a reasonable baud. You can experiment with that if you want. 57K works for me. So we have that configured on the flight controller. So that's done. Let's go back to our directions. So the flight controller is now sending, and if somebody wants to, receiving MAVLink traffic. Any bits that come on that UART port will be interpreted by the flight controller as MAVLink 2, and the flight controller will be sending out MAVLink 2 packets at a rate of around 10 hertz on that protocol, on that port. All right, so the next thing is to flash the firmware to the ESP32 board. And I do want to go back a little bit here and explain a little bit more theory of ways that we can communicate. So let's go to okay, there's a bar in the way. Let's go to the wiki for ESP32. This says Q ground control. So as I mentioned, if we go back to ArduPilot, let's go back to ArduPilot. So as I mentioned, MAVLink is very versatile. So Mission Planner is one set of software that'll interpret the MAVLink packets and present the information in a user-friendly way, but it's not the only one. MAVProxy is a command line version where you can send MAVLink commands via a command line, and you can script it. So you can write scripts to tell your drone to fly to point A, B, C, and this is how they make drone swarms. So in drone light shows. So that's another one. It's a lower level one. They're all just sending MAVLink packages back and forth. What's not shown on here are other options for ground control stations. So Q ground control is an alternative option, which is separate from ArduPilot, but uses the MAVLink protocol, and that works on Q ground control, works on ArduPilot, also Pixhawk, which is a competitor, and Q ground control works on Linux, Windows, iOS, and Android. So Q ground control is another option, and there's even apps that use MAVLink on your tablet or smartphone that if they can get connected to the drone somehow or other, they will use MAVLink and control and listen to that drone. So setting this hardware up is useful for a lot of different possible ground control stations, a lot of possible different drones. So how do we get our drone to talk? So there's a lot of hardware options. If we go to Copter, peripheral hardware, and okay, there's all these things: crop sprayer, buzzer, camera, grippers, etc. So the one, and like I said before, ArduPilot has very good documentation. So the one we want is telemetry, QRST. telemetry radio, landing page. So these are all the different pieces of hardware that you can buy that will create a wireless link between your drone and the ground control station. So there's long range, short range, etc. So let's go through them. The most popular one is this SICK 900 megahertz radio. There's lots of different versions, and it's basically a 900 megahertz modem. Okay, it's a modem. You need one on the drone and you need one on your computer, and the one on your computer plugs via USB. The one on the drone plugs via UART. So you need two of them, and they have this big 900 megahertz antenna, and then they need power, and you can get about probably 10 kilometers of range. They have about 100 milliwatts. It's just a 900 megahertz modem. It's $200, and it's a little bit heavy. Let's look at the weight. Rural range, line of sight. Okay, 100 kilometers. So that's how far I can get it. Where is the weight? Come on. Weight. I'll tell you. Well, it's too heavy for my taste. It's too big and heavy for the drones that we're building. Probably the drone could handle it, but we don't need 100 kilometers of range, and it's $200. So there's that. So that's the most popular one, and most of the student projects that have big drones that want long range, that don't want to do any fussing and don't care about budget, they buy that, they put that on their big drone. Another popular option is using the cell phone network. So these are some companies that offer solutions to connect to the 4G network. I don't endorse or have stock in any of them. Let's use any of these products. Let's use XB Station as an example. So this is a kit, and
warning, arming checks disabled.
This is
armed, disarmed. Warning, arming checks disabled. Warning, arming checks disabled. Armed, disarmed.
You have to.
Warning, arming checks disabled.
The ESCs beep if you don't arm it after 10 minutes. Okay, so here's their solution from this company, XB Station. And basically what it is, it's a Raspberry Pi. The Raspberry Pi talks over a UART to the flight controller. It's bigger. It's going to get big? No. I want it. Ugh. Okay, anyways. And then this is a Pixhawk flight controller. That's a bigger, more reliable flight controller, more expensive, a couple $100, and heavier than ours. That's the one that is sort of industrial strength flight controller. You can build aircraft with 100,000 pounds, and that'll reliably run those aircraft. Anyways, there's a Raspberry Pi, and then on board there's a 4G modem. So that's pretty heavy for my taste, but that is possible. That's a way to do it, and they'll sell you that kit. You can just buy a Raspberry Pi and buy a 4G modem, put it on there, and that would be an advanced topic in this class on a separate series of videos. One more option is Express LRS, which we're using for the radio control, which I like because the radio control receiver is only 0.44 grams and it's only 10 or 20 bucks. And it has a range of 10 to 100 kilometers. Well, the developers have tried to piggyback telemetry onto that radio control. It's called Airport. And that's another option, but you need a second Express LRS receiver, and then you need on your drone just for the telemetry, and you need an Express LRS transmitter on the ground that would talk to your computer. That's down here over USB. So the cost adds up and the complexity adds up. And you can get long range with that also, and very, very lightweight. But we're not going to do that. It's just too much work. That would be an advanced topic, and we're not doing that. What we are doing is the simple one, which is Wi-Fi. ESP32 Wi-Fi telemetry. So that's the Dronebridge one that I'm mentioning. And that's what we're going to be doing. So why did I pick this? Because this board is tiny. It's the size of a penny. It probably weighs 1 gram. It's cheap. You can get it for 12 cents on AliExpress with $3 in shipping. On Amazon, it's $10 for overnight delivery with shipping included. So this is what we're using. And it's very, very easy to configure on the drone end. And it's very easy on the ground control station because the ground control is just the Wi-Fi on your computer, which I'll show you in a bit. So that's the good news. The bad news is the range of Wi-Fi is only about 150 meters in our hands. So don't expect to go many, many kilometers with this. All right, so that's the reason we're doing it. And now I need to talk a little about this ESP32 chip. So I had skipped it before, and I'm going to come back to it. Where's the directions? So this is the name of the board, Seed Studio JAO ESP32C3. So what's an ESP32C3? Just briefly, it's from the company called Expressive. Expressive makes an ESP32 family of microcontrollers. And the C3 is the cheapest. And that's why we picked it. Because we're not doing anything. All we're doing is passing MAVLink traffic, which is very low latency. So where is 32? Come on. Well, it's one of these families. Let's do a search. And it's the most recent one. The original ones that they came out with were like 10 to 20 bucks each. The chip is, less than $1 for the chip. So let's just do ESP32C3 with Google and see what comes up. And brings us to Expressive. Here's the documents for ESP32C3. We're not going to do that. Let's do specs, data sheet. Okay, I've got a DigiKey. It's all made by Expressive, so I don't want DigiKey. I want Okay, Expressive, here's the technical reference manual. Oh my gosh, it's 800 pages. And this is the complete technical specs. It's a RISC-V microcontroller. Let's just do a Google search for ESP32C3 specs. We don't need all the details, we just want the specs. So I suppose we could even look on Wikipedia if it has to be. That's good enough for this purpose. So the CPU for the C3, it's actually a RISC-V. Oh, that's not the C3. I want the C3. All right, we'll use this. Who knows where it comes from, but I'll check it's accurate. So the CPU is a 32-bit RISC-V. It's one CPU. Memory, 400 kilobyte SRAM, external flash up to 16 megabytes. Connectivity, 2.5 gigahertz Wi-Fi, Bluetooth, etc. Peripherals, 22 input outputs, UART, SPI, I2C, I2S, PWM, ADC, TWI. So that's the microcontroller chip that you can buy, and then you want to put it onto a board, which is called Seed Studio JAO. So they take that microcontroller, they put it on a board, and let's look at that briefly. Oh, I don't want DigiKey. Okay, let's just go to the Amazon one because I'll have pictures of it. And this is what we bought for you. Okay, so here it is. $10, and here's the pictures. So That's the microcontroller. There's two buttons, one connector for the antenna, and one USB connector. That's all there is. And a very, very simple, small, easy to use microcontroller that has built-in Wi-Fi. It's tiny. There is an external antenna, and that's what we're going to be using. So, right. So, okay. Wow, it's 35 minutes. So let's get to it. So now we want to flash the firmware onto this microcontroller. Okay. Let's go to the directions. We don't need Amazon. We don't need C Studio. Keep that. So first, okay, so I'm going to unplug the drone from the computer.
GPS glitch or compass error.
Turn the battery off on the drone. Now I'm going to plug the USB
Telemetry lost.
cable into the ESP32 microcontroller. Actually, let's do the device manager while I do that. And hopefully this will come up as a COM port. Do we have any COM ports? No, we do not. So this will be the only one if it shows up. So I'm plugging it now into the USB port of the microcontroller. Okay, it's plugged in. Windows is doing its dinging. And there's a port, USB serial device COM6. So that's what we want. So we want to make sure that it's got a COM device. It does. And now we're just going to flash it. And the flashing is very easy. There's instructions. Oh, I don't want to do that. I want to do instructions on this website. Copy link. Here's the, oh, I don't want that. I want the instructions. Okay, so let's go to the website. Dronebridge ESP32. It's on GitHub. They have a link. There's some information about it here, and then there's the wiki. For further information, please check the wiki. So the wiki has a setup guide, supported hardware, wiring, install the firmware. So I'm going to click on install the firmware and follow their directions. We're going to use the official online serial flasher. So go to the installation page. We'll right click, open that. There it is. Connect the controller. We did. Follow the steps. So we have to connect, and we want this COM port that we confirmed is correct. So it's connecting. We want the most recent stable release. We're going to use ESP32C3, flash the firmware. Done. And we're flashed. So great. Now we have flashed the firmware onto the ESP32 so it can interpret MAVLink packets and pass them along. It's just passing them in one direction and passing them in the other direction. So we do have a couple more things to configure on that, which is, let's go back to the directions. So we did the flashing of the firmware. Now we need to configure it. Now, like I said, this is an ESP32 microcontroller. So it's going to create its own hotspot called Dronebridge. The password is Dronebridge. And we can log into its web browser, website, and configure it. And we need to configure the pins that we're using for the microcontroller because, there's lots of pins here. So we need to figure out which pins we're going to use. And it matters. So let's look at that. Let's see if I can get a quick picture of the pinout. Okay. Come on. I long manual. So here's the pinout of the ESP32. So which pins do we use? Well, we're going to need 5 volt and grounds to power it. And then we're going to use pins 9 and 10. That's what works for me. If you want to try other pins, be my guest. But I suggest you follow these pins because not all of them may be working. This is a, open source development project. So this is what works for me. So we're going to go configure that by going to the ESP board website. So again, we go to the wireless network, and here's its hotspot, Dronebridge. We're going to connect, and the password is Dronebridge.
Mode change to stabilize.
Yeah, it actually, because I did this before, the drone is connecting automatically to MAVLink. But let's do it again as if we've never done it. So we flashed it, now we're configuring it. And it says no internet. That's fine. So we want to go to dronebridge.local. And there's the website for the ESP32. So it hosts its own website. And you want to change these settings. So you can change the password if you want. That's going to be the Wi-Fi password when you connect with your mission planner computer. Channel 6, I forgot what that means, to be honest. I don't remember. I think that's the Wi-Fi channel. And the main things that we're doing here is the UART, TX, and RX pin, 9 and 10. Like I said, I lost it, but the pins that we solder to need to match the configuration files so that the internal software knows which pins to use. And we're doing MAVLink, 57K baud, so it matches everything else I'm leaving. So we save settings, settings change, reboot ESP32, reboot it. That's that one. So that's the configuration. And now we have to connect it. Now we have to connect the ESP32 to the flight controller. In other words, we have to make this UART wired connection. So I'm going to show you some pictures. So we're doing 9 and 10. And I'll show you some pictures from the website. So if we go to the course website, files. Oh, we're still on the Dronebridge Wi-Fi. So we want to go back to the get off the Dronebridge. Go back to my home network. Now we're back on the internet. Now I have build photos that I'm going to start populating in the Wi-Fi telemetry. And here's some actual physical pictures of the hardware. So there's the ESP32. And I've soldered onto there red for 5 volts, black for ground, yellow and white for TX and RX to pins 9 and 10. That's pin 9 and 10. You can flip it over. It's labeled on the back. We didn't even need the reset and boot buttons. Okay, there's the antenna attached. That can go anywhere because we're not going for long range. And then this is the, let's see, probably I want to just download these so I can zoom in. Download, 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 download. Okay, so this is the hands-on part of the course. It's the soldering. We don't live in a virtual world. We live in a real physical world. So you need to learn to solder and connect things. So if we go to downloads. I want this one first. Okay, so there it is, and it's taped to the frame of the flight controller. There's the wires. So that has to be soldered. The other end will be the telemetry 4-pin connector, and I always label mine. So you have ground, 5 volts, RX TX or TX RX. And we bought for you for the course pre-crimped wires so that you can slip the wires into the 4-pin black connector on one end, and the other end you have to cut the wire, strip it, and solder it to the flight controller. To the ESP32. So this is going to plug into the flight controller, and then here it is, and this is the drone, and here the telemetry 4-pin DuPont connector is plugged into the 4 pins on the flight controller, and you can even see here if you zoom in, it says TX1. So it's TX1, RX1, VCC, and ground. So it's yellow, white, red, black. So that connects it. Then you power on the drone, go to Mission Planner, and connect via UDP. So I'm going to disconnect the computer from the drone. So the drone is off now. The drone is off. It's not connected to anything. I'm going to plug the battery into the drone. The drone is on, but it's not connected to anything. Well, the radio controller, that's why it says telemetry covered. So now I want to connect it. Let's see if this works. So you're going to have to connect to the Dronebridge hotspot for Mission Planner to work. Click connect. And Mission Planner will actually automatically detect the incoming data stream on the UDP port and connect. If all goes well, let's see. And when Windows connects to the local hotspot, it worries because there's no internet connectivity. So it takes a while to check network requirements. We don't need internet connection. We just want to connect to the drone. So hopefully that will work. So let's go back here. Let's try disconnect. So now you can do auto, and it already says that there's one here, UDP port 14550 quad rotor. And we can tell it UDP by manually if you want. Click connect. Now it probably will want 57K, but it's going to automatically negotiate it.
Mode change to stabilize.
So the drone is connected over Wi-Fi. The drone is not, there's no wire connected to the drone. It's just sitting on my desk. No props, no wires, just the battery. And if I move the drone, you can see. So that's how you connect the drone to the Mission Planner with Wi-Fi. And you can use that even on the desk if you don't feel like plugging in the cable if you want. So congratulations, you have fully configured the Wi-Fi telemetry link.